Okay, we're back with E3 paper 2, starting with number 6, and it says the graph shows the variation with time t of the activity A of a sample of protactinium-234. So here's our graph showing activity in becquerels versus time in seconds, and it shows the activity, and A says, why does the activity approach a non-zero constant value? And there are two possible explanations. It's a little bit tricky because this hasn't come up yet in any of these questions. Background radiation present that is not, that's kind of still coming in towards the counter, and so that's more radiation than just the protactinium. And so that's one explanation. And then the other is that there's a systematic error in the rate counter, that the rate counter hasn't been calibrated. It also says that maybe there are other radioactive elements of a higher half-life present in the sample. I would kind of chalk that up maybe with background radiation, but that'd be pretty insightful if someone thought of that. Anyway, B, estimate the half-life of protactinium-234, explaining your work. Well, half-life counts for the amount of sample but also the activity rate. They both follow the same relationship. Both the actual count of nucleons and the activity rate follow an exponential decay, and so half-life is going to be the time when half of the counter, half of the activity is left. And so the starting activity, if we look at the graph, the starting activity is 32, but, and this is really annoying, and they're not wrong, but it says that realization that 2 becquerels is the background activity. And so this curve should really be asymptotic to 0, not asymptotic to 2. So really the whole curve is shift upwards 2 becquerels. So really the starting activity is 30 becquerels, not 32. And so really we want to see what is the time. We want to see what is the time when the activity is 15 becquerels, but we also have to acknowledge that the curve is shift upwards. So we're not going to find 15 and see where the intercept is. It looks like the intercept for 15 on the curve is right around here, which would place me at around 80 seconds. So it's not 80 seconds. We have to shift the curve downwards so that, like by about 2 becquerels. And so looking at the curve, a shift of 2 becquerels is really the intercept for 15 becquerels would actually be here, that spot, which gives me an x-intercept actually of here, which is 70 seconds for my half-life. And that agrees with the mark scheme. So there's 2 pieces of this. First of all, being able to pull the half-life from the curve, from the exponential decay curve, but also realize that the curve itself is shifted by 2 becquerels. And so if you did not realize the curve was shifted, you would have said 80 seconds. And the answer is 70 plus or minus 5. I think that's mean. But yeah, there's kind of 2 elements to that piece. They do say the 2 points if you calculate the half-life. The range accepted is 65 to 85, but it says that for the third point on that question, you have to be between 65 and 75. So there you go. I bet so many people got 2 out of 3 on that question. And that's it. That's it for number 6. Yeah, maximum mark is 4 in short questions. All right, so here's number 7. And before 7 is a little bit longer, 7 is 11 marks. 8, I've noticed that 8 actually is a repeat of number 6. So we're going to eliminate 8. So goodbye 8. But we still have number 7 to look at. So number 7. And actually, as I'm reading number 7, I see the fluorine 18, and it's talking about injecting into somebody in a medical procedure, and I realize that is also a repeat. Thank you, Question Bank, for wasting our time. All right, so let's go to number 9. Okay, so number 19 is a 15-mark question. So there's a bunch going on here. I just reviewed it. Some of it's relevant, some of it's not, but let's continue. So identify with ticks in the table, forces that can act on electrons and the forces that can act on quarks. And in the box, it says we have weak nuclear and strong nuclear. Weak nuclear has to do with particle decay, but strong nuclear is for things in the nucleus. And make up quarks make up nucleons, so quarks are in the nucleus, whereas electrons will never be in the nucleus. So for that question, quarks are both weak nuclear and strong nuclear, whereas electrons are weak nuclear only. In B, we saw this before. Similarly, we have deuterium and tritium yielding an alpha particle and a neutron. They give the atomic masses for the deuterium, the tritium, and the helium, the alpha particle. It says show that the energy released is about 18 mega electron volts. And from the data booklet, we know that a universal mass unit is 931 mega electron volts. And so it says that the energy released is about 18 mega electron volts. So first, they ran the math using universal mass units. And so we have the deuterium and the tritium, the alpha particle and the neutron, and then so you have the sum of the reactants on the left side minus the sum of the universal mass units on the right side, and we get a difference of 0.0188 universal mass units. That's this guy right here. We take that 0.0188 and multiply times the number of the amount of mega electron volts per universal mass unit that I mentioned before, and we get 17.5 mega electron volts, which is roughly 18. So in BII, they talk about specific energy. So the specific energy is the joules per kilogram, or the energy per unit mass. And so we have 0.4 kilograms of deuterium, it's 0.6 kilograms of tritium undergoing fusion. And in the first method, they use the number of nuclei that they get from Avogadro's number, the 6.02 times 10 to the 23rd. I personally like the second alternative. Makes more sense to me. So they have here, this is the 17.51 mega electron volts we found before. That's right here. And then here we need to get to joules, so that's the electron volt to joule conversion. And so 17.51 mega electron volts is 2.8 times 10 to the negative 12 joules. So that's the energy. Then we figure out the mass, and the 2.0141 and 3.0160 are for the deuterium and the tritium. But that's in universal mass units, so we have also the conversion from universal mass units to kilograms right here, and so we wind up getting 8.35 times 10 to the negative 27 kilograms. So if we want to figure out the specific energy, the energy over the mass, we divide the energy, the 2.8 times 10 to the negative 12 joules, divided by the mass, 8.35 times 10 to the negative 37 kilograms, and we wind up with 3.4 times 10 to the 14 joules per kilogram. They also allow, it does not have to be in joules per kilogram, it could also be in mega electron volts per kilogram, and they will allow that second point. This is right down there. And you wind up getting the same answer as they do for the first solution method. So that is BII. Okay, then we have C. It's hoped that nuclear fusion can be used for commercial production of energy. Outline 2 difficulties of energy produced by nuclear fusion. There's a whole slew of reasons why. Things that are wrong. It requires high temperature and pressure. You have to overcome Coulomb repulsion. It's hard to control. It's hard to actually get the energy from the process. It's hard to maintain it. It's difficult to do. But one advantage, that's CII, of energy production by nuclear fusion as compared to nuclear fission is plentiful fuel supplies, so we don't have to get large nucleus radioactive materials like uranium, and little to no major radioactive waste products. That's a big deal. From nuclear fission, we have radioactive waste that you need to deal with. With nuclear fusion, you don't. All right, D. Tritium is unstable, decays into an isotope of helium by beta minus decay. And so here's the reaction we're talking about, tritium decaying into helium by beta minus decay. So beta minus, that would just be an electron that has a Z, a proton count of -1 because it's negative. And so that works. We have one becoming, that bounces out. We have 1 becoming 2 minus 1, and that balances out. But then we have tritium, which has a nucleon count of 3, yielding helium with a nucleon count of 4, plus beta that has no nucleon count. So that doesn't match up. And so actually, the isotope is still helium, but has a nucleon count of 3, not 4. So it's going to have 2 protons and 1 neutron. And now keep in mind, they're picky here. The nucleon number, what is it? And so it says, do not accept the actual isotope of helium. It says, what is the nucleon number? And that is 3. So be careful that you give the right answer there. And then DII talks about Feynman diagrams. We do not need to worry about Feynman diagrams, so we're going to skip that. That was an old, I think that was one of the old options where we had to deal with Feynman diagrams. So we are not doing that, but we can round out this question with DIII. What fraction of tritium remains after 1 year? I think the problem did tell us what the half-life of the tritium is. The half-life is 12.3 years. So let's bring that back over here. And so we have the half-life is 12.3 years. We know that the half-life equation is natural log of 2 over the decay constant. So the decay constant is natural log of 2 over the half-life. The reason why I care is because the actual count is the original count times the e to the negative lambda over t. And so it wants the fraction of tritium. So basically I'm doing count over the original n over n naught is e to the negative lambda over t, but I can figure out lambda and I know t. So let's figure that out. And so we figure out that the decay constant is 0.0563534 years to the -1, because we're dealing with years. Good morning, Southside. Today is Tuesday, Good morning, March 25th, Southside. 2025. Okay, and so, yeah, we figure out what lambda is. The half-life is 12.3 years, so we get 0.0563534 years to the -1. Throw that in for our decay constant, throw in 1 for t, because it's 1 year, and we get e to the negative 0.0563534 is equal to 0.945205, or in other words, 94.5%, which agrees with the mark scheme. There you go. We're at 13 minutes now. I think we can squeeze in one more problem into the solution set. So for 10A, we got magnesium becoming aluminum, and it emits a beta minus particle. They give us the masses of aluminum and magnesium in universal mass units, and then they give us the universal atomic mass unit in megaelectron volts. And so they say, show that the energy that the magnesium gives off is about 2.62 megaelectron volts. This is not that tough. They give the numbers for the magnesium and for the aluminum. Take the difference between them, but the reactant and the product, multiply times the universal mass unit to megaelectron volt conversion, and we get about 2.62 megaelectron volts. And B talks about how there are some of the beta particles have an energy of 1.76 blah 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 megaelectron volts, and that's most of them, but some of them have a lower amount of energy in megaelectron volts, and then both are accompanied by gamma photons of different energies. And it says the final state is the same for both routes. State the conclusion that can be drawn from the existence of these routes. I could draw 2 conclusions, but one is, yes, the energy for nuclear energy levels, because so the fact that gammas are emitted means that the nucleus is going from an excited nuclear state to a non-excited ground state, which is the only way a gamma particle can be emitted. But the fact that there's 2 different beta particle energies also means that gives testament to the fact that the beta particles can have a variety of kinetic energies, and they actually get to this later when they talk about why is there a difference in energy is because the neutrinos emitted, that's B triple I. But I think definitely the fact that we have gamma photons and evidence for the nuclear energy levels, that really should be there. All right, then it says calculate the difference between the magnitudes of the total energy transfers in parts A and B. So B double I, difference between the magnitudes and total energy transfers in parts A and B. Part A has 2.6175 mega electron volts, we saw that. And then part B has two different routes, but if you run the numbers, it's going to be that 1.76656 plus 0.84376, and that's the same amount for both route N2, same totals. So it's the difference between the number, the 2.6175 from A, and the 2.61032 from B, giving us 0.007195 mega electron volts. I bet they're going to want us to do something with that. I also notice they actually do have the other side, the other route up here, but it comes up to the same number, 0.007195 mega electron volts. Now, B triple I, why is there a difference in parts? The difference in part B double I, why is there a difference? And the difference is because another particle, the neutrino or antineutrino, is emitted. And so the neutrinos account for the difference, the spectrum of energies that happens because of the spectrum of energies that the beta particles have, or could have. All right, C. Small amounts of magnesium in a material can be detected by firing neutrons at magnesium-26 nuclei. So for CI, we're talking about magnesium-27 detection. CI says smallest amount of that magnesium that can be detected is 1.1 times 10 to the negative 8 kilograms, and then show that small amount is about 10 to the 17 atoms. So I'm not picking up what they're putting down with this mole thing on the first explanation, but you know that it's magnesium-27, and each nucleon is 1.66 times 10 to the negative 27 kilograms. And magnesium-27 has 27 of them, so we get 4.482 times 10 to the negative 26 kilograms per nucleus of magnesium-27. So if we take 1.1 times 10 to the negative 8 kilograms and divide by the mass of 1 kilogram of magnesium-27, we get 2.45 times 10 to the 17 nuclei, which agrees with this right here. Giddy up. And CII says a sample of glass is irradiated with neutrons, so all the magnesium becomes magnesium-27. The sample has 9.5 times 10 to the 15 magnesium atoms. The decay constant is 1.22 times 10 to the negative 3 seconds to the negative 1. How many aluminum atoms are made in 10 minutes after the radiation ends? Remembering that it said before magnesium decays to aluminum. So if you're like, what are they talking about aluminum? Magnesium-27 decays to aluminum. So we have 9.5 times 10 to the 15 magnesium atoms to start, and then we have their decay constant, and it's 10 minutes. I don't know where they're getting 60 in the mark scheme. That's 10 minutes, so that's 10 times 60, that's 600 seconds. And we have to use seconds because our decay constant is using seconds. So let's see what we get. Yeah, that's a typo in the mark scheme because the answer is correct. 4.57 times 10 to the 15, that's what I got. But be careful, they asked for the aluminum, not the magnesium. So that's how much magnesium is left. So it's the difference between the starting magnesium and the end magnesium that became the aluminum atom. So the answer is not 4.57 times 10 to the 15, it's 9.5 times 10 to the 15 minus that number. So be careful when you're answering that question. All right, then C triple I is the last part of number 10 and will be the end of this video. So estimate in watts the rate at which the energy is transferred by the decay of magnesium-27 during the 10 minutes after the radiation ends. Okay, so to figure out the rate, we know that the time is 10 minutes, so that's 600 seconds. So that's easy, but we need to know the energy. And so it says the energy released is the number of aluminum nuclei created, which we figured out. That was the 4.93 times 10 to the 15. then the 2.62 times 10 to the 6, where the heck is that coming from? That comes from all the way back in the beginning when it says that that the energy released in the decay of one magnesium-27 nucleus is 2.62 megaelectron volts, all the way back at 10A. So great. And then, yeah, so we have the 4.93 times 10 to the 15 times the 2.62 times 10 to the 6, and then we want to get into joules, so we have the electron volt to joule conversion right here, and that gets us 2100 joules. It would be 2066.66 joules. That divided by the 600 seconds gets us 3.44 watts. So they say 3.4 to 3.5 watts. Sounds good. All right, so that was number 10, and we are overtime. So 11 and 12 will have to wait. Let's see, the polonium. Yeah, that looks like that's not a repeat. Anyway, so yeah, that was. Let's see, two of them are repeats. So we're going from number 6. We're skipping 7 and 8. Then we have 9 and 10. So that would be 6, 9, and 10. Okay, thank you.